All right, welcome back. Today, we are tackling a classic curveball from organic chemistry. Seriously, this is a concept that feels like it was specifically designed to trip you up on exams. It's called the Ortho effect, and it's a perfect example of when chemistry's rules seem to, well, break. So let's dive in and figure out exactly why this happens.
I mean, think about it. You spend all this time learning the fundamental principles of how molecules are supposed to behave, right? You build this solid foundation, and then you hit a problem where following those exact rules gives you the completely wrong answer. It's super frustrating, but you know what? It also points to something much deeper going on.
And this is the toolkit we're all taught to use, isn't it? You look at a molecule and you start analyzing the electronic effects. Is a group pushing electrons or pulling them? You use inductive and mesomeric effects or resonance to predict how acidic or basic something's going to be. And look, 90% of the time, this works like a charm.
So let's put that toolkit to the test with a classic example, the toluic acids. All these are is benzoic acid with a methyl group stuck on it. And there are 3 different positions it can be: ortho, meta, and para. Seems simple enough, right?
Okay, so let's try to reason this out using our standard rules. We know a methyl group is electron donating. So what does that do to acidity? Well, donating electrons destabilizes the conjugate base. That's the negative ion left behind after the acid gives up its proton. And a less stable conjugate base means you have a weaker acid. Since this electronic effect is strongest at the ortho and para positions, we totally predict those isomers to be the weakest acid.
But here is the trap. On the left, that's our prediction, with the ortho isomers sitting there in dead last. But the actual experimentally measured order on the right shows the complete opposite. The ortho isomer isn't the weakest, it is the strongest of them all. Stronger even than regular benzoic acid.
So what on earth is going on here? How can our reliable rules get it so spectacularly wrong? This isn't a mistake in our textbook. It's a huge clue that there's another, more powerful effect that's completely taking over.
And that phenomenon, my friends, has a name: the ortho effect. And it's this fascinating case where the physical size and the crowding of atoms, what we chemists call sterics, just completely overpowers all those electronic effects we usually rely on.
So here's the formal definition for you. It's a special effect, and it really only applies to groups at the ortho position, that's the spot right next door to the main group, on 2 main types of molecules. So let's see how this plays out. First up, benzoic acids, and then we'll look at anilines.
So in the case of our benzoic acids, the ortho effect works through a mechanism with a pretty cool acronym, SIR or SIR. It stands for steric inhibition of resonance.
Let's just break that name down. Steric inhibition basically means that crowding is physically stopping something from happening. And what's it stopping? Resonance. That bulky group sitting in the ortho position literally bumps into the carboxylic acid group. It's like they're fighting for space, and it forces the acid group to twist out of alignment with the flat benzene ring. It's actually a brilliant chain reaction. It all starts with simple repulsion. The groups are just too close for comfort. To get some breathing room, the COOH group is forced to rotate, twisting out of the ring's plane. Now, that physical twist breaks the electronic connection. It breaks the resonance. And here is the key. The benzene ring is normally electron donating, which, remember, weakens the acid. By breaking that connection, we completely remove that weakening effect. And if you take away something that makes an acid weaker, well, it becomes stronger by default.
Okay, so that's how it works for acids. But what about bases, like aniline? Well, the ortho effect is definitely at play here too, but it works through a slightly different mechanism called SIP, or SIP.
SIP stands for steric inhibition of protonation. So this time, the crowding isn't just messing with resonance, it's inhibiting the very thing that makes something a base, which is accepting a proton. You can almost think of the bulky ortho group like a bodyguard, physically getting in the way and making it incredibly difficult for a proton to even get close to that nitrogen atom.
So here's the play-by-play. For aniline to act as a base, it's got to accept a proton. But when it does that, the nitrogen group actually gets bulkier, and that creates even more crowding with the ortho group next door. This makes the resulting ion incredibly unstable. The molecule just hates being in this crowded state, so it's way less likely to accept that proton in the first place, and that of course makes it a much, much weaker base.
And just look at what this does to the ranking. For the toluidines, that's just aniline with a methyl group, the ortho isomer is now, by a long shot, the weakest base. It's a total reversal of what we saw with the acids. The ortho effect makes acids stronger, and it makes bases weaker.
Now, just when you think you've finally got it all figured out,
chemistry loves to throw one last gotcha moment at you. There is an exception to the exception, and its name is salicylic acid.
So what's the deal here? Salicylic acid has an OH group at that ortho position. So yeah, the SIR effect is definitely active, which helps make it a strong acid. But it has a secret weapon. After the acid loses its proton, it forms that negative conjugate base, and that negative charge is perfectly stabilized by a hydrogen bond from its neighbor, the OH group. Think of it like a built-in safety net. This extra stability makes it incredibly easy for the molecule to give up its proton, making it a truly, exceptionally strong acid.
Okay, I know that was a lot to take in, so let's boil it all down into a simple, practical cheat sheet that you can use to absolutely nail these questions every single time.
And here it is. It really just comes down to two simple rules. For any substituted benzoic acid, the ortho isomer will always be the strongest acid. The reason? SIR. And for any substituted aniline, the ortho isomer will always be the weakest base. The reason? CYP. That's it. That's the whole key to defeating this exam trap.
So, the crucial point, the main takeaway, is this. When you see a group at the ortho position on a benzoic acid or an aniline, you need to just stop thinking about electronics for a second and start thinking about physical space. In these specific cases, steric hindrance, the sheer bulk of the atoms, is king, and it overrides everything else.
You know, mastering an exception like the ortho effect is about more than just memorizing a fact for a test. It's about learning that science is full of these incredible layers. The rules you learn at first are powerful, for sure, but it's in the exceptions where the deepest understanding really lies. And that leaves you with a really fascinating question. What other fundamental rules that we take for granted are just a simplified version of a much more complex and interesting reality?